Okay, so thank you for inviting me. So I guess that I'm a little bit of the guy in between in this talk. I'm very happy to be talking at VSS that actually, as an industry guy now, but this was my conference. I think I've been in this community since first Arbor 1998. So I've seen the transition to VSS. I was chairing also ECVP 10 years ago, and I did the leap some time ago to this crazy world. We're having a lot of fun. So thanks a lot for having me here. It's a great time for me to be back where I was for a long time. And actually, my postdoc advisor is the president of this conference right now. So, yeah, I'm going to be talking about a few issues, and actually, my talk is going to build up on some of the previous talks, because everything that our HoloLens colleague talked about holds for us as well. Even Emily's stuff is very relevant to us. And this is a brainstorm that I've been working on with Mojian, my main colleague at Meta. She's in the first row if you want to talk to her. And I'm going to be talking about the interaction between human vision science and AR. So in my talk, I will quickly introduce Meta, especially the Meta 2 developer kit, talking about why we need to care about vision science and why vision science may care about AR, and then what type of research takes for what kind of deep research vision science can give to the development of augmented reality products that are still at the early stage. We need to admit that, okay? It's coming, but it's coming after a while, and this community can give a lot to that development. Okay, what is the Meta 2 developer kit? You see it here. So what are the main features? It's got 90 degrees field of view. This is the main feature, the main even on the competitive, we don't like to talk about competitors, but in the several products landscape, we are by far the largest field of view available. In terms of resolution, we have 25 pixels per degree. We have a front-facing camera like the HoloLens. We have a depth sensor for tracking, and we mainly use for tracking hands. We have a sensor array for object and environment tracking that enables us, and an IMU, 6 degrees of freedom, that enables us to build the SLAM technology. SLAM stands for simultaneous localization and mapping. It's a computer vision algorithm that tracks the features over time in an environment, and this is used to lock virtual objects in that physical space. We got 4 speakers for near-ear audio and microphones as well. We have a transparent visor. We care about eye contact because collaboration is one of the major use cases of augmented reality. So what you see here is actually what you see in our headset, okay? It's wearable along with prescription glasses for some of the previous questions that I've heard. You can put your prescription glasses, and I'm anticipating some of the questions. You can put some eye tracking glasses like Tobis or SMI, and you can wear it along, and you can sync them up if you need to for your research. It's tethered. We want to exploit the full functionality of a powerful machine at this stage, and it's got a 9-foot cable. It takes a VR-grade computer, and so it's a powerful Windows machine to drive it, okay? And it's, for now, it's a Unity-based SDK with C# engine as well. Okay, why vision science and AR? Because we're shoving computers, Emily said before, we're shoving computers to our eyes. So we need to care a lot about the eye components. The industry wants us to deliver a fantastic experience on the right-hand side. And we need to solve, and what the vision and sensory science community can give is solving the puzzle, the maze that is in between. And it's a huge maze, okay? This is what I'm going to represent in the next slide. There was a fantastic session on ensemble statistics. You have to grasp the ensemble here, not the details. But those are the teams. Okay, I did an exercise a few months ago. I went through the VSS program and sessions, and I see how it could connect to our product, okay, and to our research, because we do research in our department. binocular and depth vision. I don't have to say much. Emily and other colleagues before talked extensively about that. Peripheral vision. Peripheral vision is another very important aspect of the development of augmented reality for a number of reasons, one of which I'll go a little deeper later. Attention is very important. It's also a very practical reason. If people's gonna wear this device and replace their phone or their computer with this device, we need to understand, how the digital and real world are gonna interact. Even on an attentional standpoint, it's a simple safety features, if you wish. Face perception. Face perception is important because you can also have like a remote call with your 3D colleague from the other part of the world. How do we want to render faces? How do we want to show faces? This is a reason why even our hardware is free from eyebrows down, okay? So there are issues around that for remote and in-person collaboration use cases. There's a lot of issues around multi-sensory perception in the audiovisual, vision touch, vision vestibular, visual and proprioceptive. We have manipulation of virtual objects in our product. This is another distinctive aspects of Meta 2. But what is important to do, we don't have haptic, we have proprioception, we have vision, 3D vision, stereo vision and proprioception. How much can we push on that? When do we have to put up a haptics in? How much haptics is important? This is fundamental research that needs to be performed, okay? Spatial vision, of course, there's a lot of stuff around spatial vision, very basic aspects, and it's useful. Contrast, acuity, and so forth. There's many things around objects and scenes, from reading, if it's object perception to you, the object formation and object realness. I'll give examples in the rest of my talk. The way you integrate objects, real and digital objects. Scene perception, the way you cast illumination in your digital world, because there's also illumination for the real world. Material perception, what kind of material identity you give into your digital content, and so forth. Perception and action is big, because we want to go and grasp, we want to do Minority Report. So there's a lot of perception and action topics here. I'm not going in depth, because this slide otherwise is going to kill the rest of my talk. There's many things around clinical vision, both on the optometric world and in the neuropsychology and individual differences. And there's other important aspects like one overall time perception, where our rendering pipeline and the real time, and the fact that augmented reality doesn't forgive way less than virtual reality, because in virtual reality you can offset in time and space the entire scene. In augmented reality you get the real world as a reference, and it's a very non-forgiving reference for your virtual object. Anytime you move your head, as Microsoft pointed out and worked very well towards, it's very important to have stable objects. And time perception is a very important topic to expand on for this product. So, in the rest of my talk, I'm gonna talk, in this section of my talk, I'm gonna talk about how vision science can contribute to the AR product. One aspect is setting up the product requirements. We engineer up to the point that the human sensory motor performance requires, right? Then, if my computer moves on. Okay. Simply, mastering psychophysics is very important. Provides not only psychophysics, but mainly psychophysics, important tools, even because with psychophysics, you can talk to all the engineering teams, mainly computer vision, with the same language and set metrics that are important mutually. Understanding individuals and individual differences. So user characterization is another important contribution that vision science can give. And also how perception steps in different parts of the process of producing AR product. My key. All right. For the first, okay. In the first of these 4 bullet points, I want to talk about foveated rendering and how foveated rendering. What is foveated rendering? is a technology that renders, once you know where the user is gazing at, renders the rest of the display so to follow what peripheral vision sees, right? Point is, what it's solidly known, especially to engineers, about peripheral vision is the optical, maybe the receptor subsampling, everything that's in the eye. But there's way more to that. I had a conversation with Bo about Strasburger's article about peripheral vision in Journal of Vision. It's 87 pages, and it talks about just one aspect of peripheral vision. Peripheral and ensemble statistics, old Symposium today was a lot about that. So peripheral vision is way more intricate than just pixelating the periphery. And what do we have to know? How do we treat with that? So I'm stealing a little bit the stage to the NVIDIA speaker after, but we stole this from one of their very important demos because they are the company that have gone the farthest in this foveated rendering. Why foveated rendering? Because virtual and augmented reality requires a lot of pixels to render at high resolution over a very wide field of view. And modern displays and modern GPUs, they cannot stand that in real time, right? So this is the foveated rendering. Oops. It doesn't like. Okay. If it doesn't go, I'll let it. All right. So this is their best, this is their latest known iteration, and it's contrast preserving. So in that case, the user doesn't see, because in previous iteration of foveated rendering display, if you're pixelating the periphery, you notice that. It's bad experience. They iterated and created like perceptual effects. How far do these perceptual effects go? How much time do I have? All right. There's several aspects of I canceled one slide, but it is fine. There's several aspects to take into account. One is that peripheral vision, our tasks are acute in the periphery, depends on the task, depends on the stimulus. This is one thing. Another thing is that this is just a quick movie from one of my latest papers in my basic science live, in which we show like the spatiotemporal remapping. So we're going to remap, not only we're remapping the next saccadic location in space, but we're doing it in time as well. So there's some spatiotemporal warping that we have to take into account, because it may be that even real time is not enough to render in the periphery. So we have to know exactly how we're going to use and what kind of information we're going to use for our next eye movement. Plus, there's effects in which we overshoot. If we have to match a peripheral target to a foveal reference, we always overshoot. We always say that it's sharper than it actually is. So there might be a decisional effect, but still is a peripheral effect that shows that things are not just explained by the optics of the eye, right? So in the second case is the use of psychophysics. This is just showing something that is very simple to you, but I published, this is my first paper as an applied scientist, in which with Meta1, our first product, I was trying to figure out how well we're displaying stereograms in depth, just by matching my stimulus to a physical probe at various base depth. And what I found out is that for that specific product, there was a constant offset, so we corrected for that offset, and that was constant no matter what the base depth was. So we made that correction, and I used psychophysics for that. Very good. The computer vision, the engineers liked that a lot. Okay, I didn't give like a ballpark estimate. I gave them a very accurate estimate. User characterization. We need to know how stereo vision works, okay? There's a lot of factors that impact on our stereo acuity. I'm not going through that. You guys are teaching me that, actually. But there's several components, and those several components actually contribute to create a whole like ecosystem of individual differences over many different dimensions. In fact, we know from this progenic study from Cambridge that 10% of a white population failed cross-disparity test, another 10% fails on cross-disparity test, and less than 30% of the people are not ideal in stereo vision. And those are technologies heavily based on stereo vision. So point is, we know, I mean, the industry knows that when you have bimodal customer reviews, that is going to kill the product, okay? So we need to, as Emily said before me, we need to create products that actually are very good for a wide variety of the population, or maybe thinking about versioning, right? Then, where do vision scientists fit in the AI organization? In many different places. First, in the sensory output, optical quality, display quality, brightness, contrast, color profiles, rendering, audio, haptic simulation. But then we work with people that work on sensor and select sensors. And sensors is how we set up the array, how we decide what sensor we want to use. Eye tracker, yes or not, for example. What is the scope, the actual scope of the sensor to match human performance? Signal to noise ratio of our sensor will determine performance too. What physiological in the future, do we want to have EEG as many people are buzzing about in the industry? Does it make sense? And so forth. We are important in the ergonomics pipeline. Why? Because if we design it wrong for the head, our optical engine is gonna put the image out of the so-called eye box. We're not gonna receive the image right, and it's an ergonomic problem. So we have to step in the ergonomics team, the industrial design team, and work with them about it, okay? Algorithms. Algorithms is all the computer vision that supports the product. I'm going fast. Interaction, user experience. Those are the acronyms for that, UI and UX. There's a lot of design of interfaces that we help. And at the product stage, when the product is almost ready, we go there and benchmark it again with a lot of, with big samples, basically. I'm going fast because now I want to talk about how AR can support human vision. This is the last part of my talk. And I'm making two examples. One is object realness, and the other is natural system analysis for two different reasons. So object realness is a topic that actually Jacqueline Snow is sitting there, is working on very hard at University of Nevada, Reno. And here I'm showing two example data to show that as you, in the left plot, it shows that basically for a number of like memory, free recall, and recognition, if you have a very similar retinal image, but one is more like a line drawing, and then you go from line drawing to color and to real object, so physical object, graspable object ideally, performance is much better with real object, and you get intermediate performance with photographs, and the worst performance is with line drawings, okay? On the right-hand side, it shows for a visual search task that actually if the object is actionable, if you can go and grasp it, if you can perform an action to that object, your performance is better, okay? So the question is, and this is a question that we're trying to help Jackie with our team. We're trying to do basic research with them and use AR with manipulable objects to figure out where 3D stereo and manipulable stereo creates, at what point of this continuum the AR or VR image is. This is very important question to validate the science that Jackie's team is working on, and it bounces back to us because we're gonna know exactly what type of interactions we want to set in our product in the future, okay? In terms of natural system analysis, I'll go fast, there's a lot of words, but natural system analysis is an approach that I love to have. That was like almost 10 years ago, I started reading Bill Geisler's paper and the related papers. And natural system analysis is basically a way of saying, let's go study vision in context and study as a system, natural scene plus natural tasks together as a system. Because what we find in the lab sometimes, you know, it's not reproduced as we go out in the world. So it's important to figure out how behavior works when you have constraints, when you have priors imposed, when you have distributions imposed from the external world. For example, these are the distributions of disparities and of distances that you encounter as you walk in a forest, right? Natural system analysis requires methods for identifying and characterizing natural tasks, a definition of the environment statistics, a model for the interaction between the user and the environment, and a technology and methods to characterize this interaction. AR is a natural solution for, it's the technology for that, because you can collect data from all those sensors. If it hasn't been clear to you, you can collect depth maps, you can collect RGB, you can collect user interactions, you know where the hands are, and you may know where the eyes are falling, and so forth. So you have an incredibly rich data set for the same, for a well-known environment, and you can put artificial stimuli in it. So let me conclude. AR and VR are heavily founded on perceptual interfaces. Sensory science are linked to AR and VR research and development, but even product at several stages of the pipeline. AR and VR products are unique, groundbreaking research tools for vision and sensory science. And this new intersection between science and industry is creating new, very exciting opportunities. We're gonna be, if you're curious now, we're gonna be demoing at demo night. I finished, thank you.
We have time for some questions.
I was too clear, wasn't I?
Yeah, we're looking forward to seeing your demos at demo night.